So let's begin. Welcome, everyone. This session, our topic is BGP routing security. We all know that the BGP route security is crucial for the internet. For this session, we have 3 presentations. They will explore BGP security from 3 different perspectives. The first topic is about establishing a more secure BGP security protocol. The second topic is about detecting BGP hijacking incidents. And the third topic is about injecting cyberprefix hijacking invisible to public monitors. So let's start. Our first title is Secure Internet Domain Routing and Forwarding via Verifiable Routing Origin and FCBGP. The presenter is Zhotao Liu. Zhotao Liu is an associate professor in Tsinghua University. Prior to Tsinghua, he was a technical lead at Google, managing Google's massive scale data center networks. His primary research interests are secure internet architecture, data security and privacy, applied cryptography, and blockchain. In recent years, he has published over 30 papers on top-tier academic conferences like IEEE, SNP, SMCCS, and his research received many awards. So let's welcome Zhotao Liu.
Hi, folks. Good afternoon. Today I'm gonna discuss this FCBGP to all you guys. So I have been sharing this talk in IETF 118 in Prague last year. So if someone happy to see this before, so we'll have something new today actually. So this is a collective work from multiple co-authors, including myself, Professor Xu Ke, Professor Li Qi, Professor Wu Jianping, and Wang Xiaoliang. Let's get started. Let's start with a bit of problem statement. So we all know that the current internet interdomain routing is vulnerable. It has vulnerabilities in both control plane and data plane. On the control plane, there is no built-in mechanisms that is widely deployed to verify the BGP announcement. Because of that, the adversary could manipulate the BGP path to hijack traffic. So on the data plane, the actual forwarding path may not be consistent with the BGP path, which raises security issues. So over the past decades, actually, both the academia and the industry have made significant research in this regard. For instance, this can be placed into 3 categories. The first category is the security enhancement of the original BGP protocol, among which are 2 famous protocol, RPKI and the BGP-SAC, that are being standardized by the IETF. In the forwarding path validation, there are a bunch of academic research, such as the Young Future Internet Architecture initiated by Professor Andrew Parrick from ETH and the CMU. And also there are some research on source validation. The representative work is the Sava architecture that has been worked by our team at Tsinghua University for many years. However, but even with all this effort, the security issues of interdomain routing still persistent. Probably because of the lack of deployment due to the lack of incentives or other practical issues such as this incompatibility with the current internet architecture. So today, I'm gonna present FCBGP, hopefully to improve the state of the art of secure interdomain routing. And specifically, we have these design goals in mind. So on the control plane, in the full deployment case, we hope that FCBGP can guarantee that any BGP path authenticated by our protocol is the real BGP path announced by all the on-path ASs. That means it is infeasible for an adversary to claim that a forged BGP path is authenticated. In case of partial deployment, we hope that the FC BGP is fully compatible with the native BGP. And it is also incrementally deployable, which means the FC BGP will provide strictly positive security benefits for BGP paths whose on-path ASs are not fully upgraded. We hope that this compatibility and incrementally deployability will incentivize further deployment, so we can move from the partial deployment to the full deployment case. And on the data plane, we hope that the unwanted traffic, which means the traffic that were not sent over the desired path, it's either spoofed or sent via an undesired path, can be detected by these ASs. And this AS can then take any actions based on their own policies. So before we dive into this protocol, let's first give some assumptions and background scope to understand this, how gonna we approach this problem. So first, we assume that ASs have an access to the internet scale trust base, namely the resource public key infrastructure like RPKI, that can store the authoritative information about the mapping between AS numbers and their IP prefixes, as well as their public keys. As the ROA is becoming, the deployment of ROA is increasing, I think this assumption is becoming more and more true. Probably in a few years, we could see a very high rate of ROA. And also the multipass forwarding cost because of the traffic engineering is not considered to be a validation of data plane security. So that means if the ASs do some multipass forwarding, such as traffic engineering for optimizations, we think that is okay. We think that is not a security issue. And for the adversary, we consider a very strong adversary that can interpret all the BGP updates. So we hope the adversary can collect the BGP announcement from multiple ASs and do arbitrary analysis and stuff like that. So on the control plane, the adversary can launch path manipulation attacks, such as hijack a BGP path with a shorter path. On the data plane, the adversary can spoof the source addresses or reroute the traffic to other ASs that is preferred by the adversary. And also, we assume that the two compromised ASs will not collude, because otherwise they could share their private keys and behave as a single entity, and then it will be very difficult to derive any security guarantees, at least from an academic perspective. So let's get into this protocol. So the FCBGP was built upon a primitive called verifiable routing commitment, or we can call it FC. So let's suppose an ASB receiving a BGP update for prefix P from its neighbor A, and the ASB will use the following verifiable routing commitment, or FC, to publicly certify its routing intent over the next hop to ESC. So the generation of this forwarding commitment is actually very straightforward. So we can see from this. Formula, it's saying, okay, the ASB, it is signed by the ASB saying, okay, I accept and route advertisement from ASA, and I would like to extend this path to my neighbor ASC. And afterwards, after it generates this FC, it will put this new FC to a new BGP path attribute and send this entire BGP update to its neighbor ASC. So based on this construction, we can say at a very high level, FC BGP adopts a per pathlate validation scheme, because each AS only care about its next hops and directly connected hops. It only cares about the ASA. For instance, ASB only care about the ASA and ASC. It does not care about any AS beyond its neighbors. So it's a per path validation. This is different from the per path validation scheme, which everybody is know about. It's like the BGP-SEC. In BGP-SEC, every AS has to recursively sign the entire path. So we argue that this per pathlate validation scheme has two benefits over the per path validation scheme. The first one is, in case of full deployment, we can prove that the FC BGP has the same security guarantee as the BGP. I will show some proof later on. And in case of partial deployment, that means that but the FC-BGP will have lower path validation overhead in dynamic networks like the internet. I also have some quantities later on. In the case of partial deployment, we will show that with data-driven analysis that the FC-BGP provide strictly more security benefits than BGP-SEC. And second, also the routing intent is in form of FCs does not disclose actual information about routing policies. So that means the generating FCs will not disclose any private information about the routing policies of each AS. So as we discussed before, the FC-BGP does not modify the AS path attribute. Instead, it defines a new transitive path attribute to carry FCs. This is because of this, the legacy ASs can forward this attribute to its neighbors without changing any protocol. If this legacy AS does not understand the FC-BGP attribute, that's fine because it's transitive. Therefore, we think FC-BGP is natively compatible with the BGP. This is very different from BGP-SEC, which replaces the AS path attribute with a new secure path attribute. That means if the legacy AS will probably discard this BGP update if it does not understand this new AS path attribute. With the FC, the BGP path validation protocol is as follows. So in case of full deployment, where every on-path AS generates FCs, the ASs only need to check that there exists a FC for each individual passlet on the path. For instance, in this case, the ASD needs to check actually three passlets, sorry. The first passlet is from ASA issued to ASB, and the second passlet is from ASB issued by ASB, and third passlet is issued by ASC. So if the entire AS path, every passlet on the path has a corresponding FCs, the validation passed. In the case of partial deployment, the AS path may traverse an undeployed zone where all ASs in this room does not understand FC-BGP. But that's fine because we have this path attribute to be transitive, and this FCs can be traversed through this undeployed zone and finally reach the destination ASD. So in this case, although ASD cannot authenticate the full path, it can still authenticate some of the hops on this path. As a result, in this case, if the ASE claims that it has a direct link from ASA, the ASD gonna reject this claim because the ASA certifies routing intent to ASB, not ASE. So we also do some measurement about the overhead of the commitment generation. We used the KIDA dataset in September 2023, and we measured the busiest AS. That is the AS generated the highest number of BGP updates, which is the AS 6939. It needs to generate about 138 million round commitments in 1 month. And we then measure, okay, the overhead of generating a single forwarding commitment is roughly about 1.3 millisecond, and that means it takes roughly 71 minutes to generate all these 100 million FCs. But actually, these FCs are actually generated over a 1 month period. So we think the overhead is kind of negligible. And there are also some internet scale evaluations here. We analyzed the KIDA BGP update announcement dataset from June to September 2023. We see that roughly 65% of BGP updates are path change updates, within which over 36 of the 2-hop passlet remains the same. That means for all these updates, if the passlet remains the same, we does not need to revalidate this passlet. So we can conclude that the passlet-based path validation has much smaller dynamic verification overhead because a lot of the passlet will actually remains the same. So even if the BGP update changes, only change part of the path, not the entire path. So that means if the passlet does not change, we do not need to revalidate this passlet. Okay, in the following segment, I will provide some security analysis for FCBGP as I promised. It is a kind of somewhat not intuitive for the security analysis, but let me try to summarize the main result. And for further reading, if you guys are interested, please refer to our preprint available on our archive. Let me first declare some very high-level security analysis result. In the case of full deployment, we prove that any ASs, any pass that can be validated by. So FCBGP adopts a per passlet validation scheme. So then the adversary is motivated to strategically combine different FCs from different paths so that it can try to forge a new path. But we prove that any path that can be validated by strategically combining FCs is actually a legitimate path announced by all all the unpassed ASs. That means if the adversary can strategically combine these FCs to prove a path, to authenticate path, then this path is actually the real path. The caveat is that we still need the non-coding assumptions, and meanwhile, there might be some replay attacks which can be solved via proper timestamps in FCBGP. By the way, the replay attacks is the same as the replay attack as the BGP-SEC. It's like every distributed protocol have this problem, have this replay attack issue. And in case of partial deployment, we mean that because FCBGP is fully compatible with native BGP, so the authenticated passes can be passed along the way while we extending the BGP pass. And in this case, we prove an important lemma, saying that if the consecutive deployment is sufficiently long, the entire pass is secured, even if some of the unpassed ASs are not upgraded. So in this case, we prove that if the deployment chain from AS1 to ASK is sufficiently long, then this path is fully secured, even if the ASK and some other ASs does not deploy FCBGP. But in reality, how to quantify this partial how to quantify the security benefits in this partial deployment? We do the following experiment to quantify this security benefits. First, we sort the ASs according to the number of their neighbors. And then we, given a deployment rate, we select the top R rate ASs to deploy FCBGP. Then for all the BGP updates in the KDA dataset, we check whether the adversary can still hijack a BGP update by constructing a forged but shorter path. Then we report the hijack rate for different deployment rates. So let's see from the figure, we can see that even at the deployment rate of like 1.5%, we can see the FCBGP can prevent the hijack rate to reduce the hijack rate to roughly 20% lower than the BGP-SEC protocol. So the key takeaway is that the FCBGP as a per passlet path validation scheme provides strictly more security benefits than the BGP-SEC in partial deployment. Finally, I want to discuss a bit about the forwarding path validation here. By back propagating the verifiable routing commitment in FCBGP, the unpassed ASs can learn the desired forwarding path on the data plane. As a result, if the ASs receive traffic that violates this desired path, they can enforce certain security policies on this traffic, such as discarding this traffic or even such as lower priority forwarding or even discarding this traffic. And further, if we extend the back propagation to broadcasting, then off-path ASs can also participate in the forwarding validation. So to conclude, we can say FCBGP is a novel security interdomain routing system that can simultaneously authenticate BGP routing updates and validate data plane forwarding in an efficient and incrementally deployable manner. So FCBGP is built upon a unified primitive named verifiable routing commitment to enhance the security of control plane forwarding, control plane routing, and data plane forwarding. And third, FCBGP is fully compatible with the BGP and incrementally deployable by offering strictly positive security benefits in partial deployment. And we proved that FCBGP has same security guarantees as BGP-SAC in full deployment, and meanwhile, it imposing much smaller verification overhead. So for additional details, you can either email to me, you can send an email to me, or watch the or read this IETF draft, which is very high level, but still that has more information than I present today. And also we put our preprint available on this archive, so you feel free to check this out as well. Thank you.
Thanks, Zhou Tao, for his wonderful presentation. So is there any question?
I had probably two questions. First one is, how does this compare or differ to ASPA, which seems to be, you know, a more mature form of path verification?
That's the first question. Okay,
that's my first question.
Okay,
yeah.
So SPA is one who allowed someone to put its neighbor information to the RPK object, which is currently being standardized in IETF. So the key difference between FCBGP and the ASPA is that ASPA is the FCBGP is a to secure the entire path while we extending the BGP update. But ASPA, but for the ASPA, it just registered this object to the RPKI stuff. That's the key difference while they were on the real deployment case. But more importantly, the ASP does not prevent really prevent path hijack. It is more to prevent route leak. So that means even if the adversary can still use the ASPA object to send or to broadcast run BGP updates, and which will even if with this ASPA, the AS will not be able to verify the correctness of this BGP path according only by the ASPA object.
Okay, thank you. The second question was about the performance overhead. You had some slides further back, I think maybe slide 9 or this one, yeah. How would all right, let me restate this. For actual hardware like routers and in the wild,
yeah,
could those also handle this performance overhead?
That's the same question I received from IETF, which is, yeah, the question is right. The hardware cannot handle this well, because a lot of the router hardware is very limited. So what do we claim here is like we hope that the deployment of FCBGP is not everywhere. So we prefer only certain ASs that are very sophisticated in their technology can have the resource to upgrade their routers. So in the future, we hope that by only upgrading part of the like the important or large ASs, we can have a large fraction of protection rate in the future.
I think a follow-up to that, I guess one of the nice things about route origin validation with RPKI is the actual cryptography part can be offloaded to a validator. And I'm wondering if there's any way you could implement a similar strategy here somehow for the cryptographic verification to be done by a system with that capability, and then just submit the results back to the actual network device.
Yeah, that's a great question. We currently are negotiating with some IXPs to further deployment, and the first step deployment was deploying stuff on their routing reflectors. So, yeah, that's a great point.
Okay, all right, thank you.
Thank you.
Is there any question? So okay, thanks, Zhou Tao, for his speaking. So let's move to our next topic. Our second topic is accelerating the detection of BGP origin hijacking by distinguishing legitimate and illegitimate modes. The presenter is Lan Chengqin. Lan Chengqin is a PhD student at Tsinghua University. His research interests include BGP security, source address validation, and network measurement. His research work has been published by Usenik Security and NDSS. He is also active in ITF subnet working group. So let's welcome Chinan. Sorry. Yeah, let's welcome.
Okay, thanks. Hello everyone. I'm Lan Chengqin from Tsinghua University. I'm going to introduce one of my research work related to BGP security. My research interests include BGP security, source address validation, and network measurement. And this work has been published in Usenik Security 2022. Okay, the paper title is SAMIS, Accelerating the Detection of Route Origin Hijacking by Distinguishing Legitimate and Illegitimate modes. BGP origin hijacking is the most commonly observed type of BGP hijacking. There are two kinds of BGP origin hijacking. There are exact prefix origin hijacking and subprefix origin hijacking. The exact prefix origin hijacking means the hijacker announces the same prefix of the victim in BGP, while the subprefix origin hijacking means the hijacker announces a subprefix of the victim in BGP. Both kinds of origin hijacking usually do not last long, but can cause serious routing and security problems, such as traffic disruption and financial losses. In 2021, BGP-Mon detected more than 700 major BGP router hijacking incidents, resulting in large-scale network outages. So, to mitigate BGP origin hijacking, there are many BGP security mechanisms. They can be divided into two major classes. The first class is proactive prevention mechanisms, such as IPKI. These solutions usually use cryptography to authorize all legitimate origin aliases for the prefix in advance to prevent origin hijacking. However, these mechanisms are fully effective only when deployed by all aliases, which is still a long way to go. So, in current stage, many network operators would like to use reactive detection mechanisms, such as augurs. This kind of solutions usually monitor BGP updates from multiple BGP monitors worldwide and raise alarms when detecting origin hijackings. For example, the state-of-the-art solution, that is augurs, combines both control plane analysis and data plane probing to make the final decision. Specifically, in the control plane, it detects all multiple origin aliases, MOAs, based on historical BGP data. MOAs is a special phenomenon in BGP when multiple aliases originate the same IP address block. And then in the data plane, it uses trace routes or PIN and even manual verification for each MOAS conflict to identify real origin hijackings. However, we found that most MOAS conflicts are legitimate MOAS. So what is legitimate MOAS? Legitimate MOAS is a phenomenon in which a prefix is legitimately announced by multiple origin aliases simultaneously. They can caused by business corporation, IP address transfer, or DDoS protection, and so on. So current BGP hijacking detection mechanisms cannot effectively distinguish legitimate modes from hijacking only by control plane information. Therefore, data plane probing or even manual verification is still necessary. However, because legitimate modes happens more frequently than origin hijacking, massive false positives from the control plane greatly increase the verification cost and the verification latency. Considering 1 minute latency may cause high financial losses, existing BGP detection mechanisms would have higher verification cost and result in very high financial losses. So this work aims to accelerate the detection of route origin hijacking. First, we identify the potential causes of legitimate MOAS conflicts and the behavioral features of real hijackings. Then we train a machine learning classifier to distinguish legitimate MOAS and origin hijacking based on control plane information. And finally, we propose a new origin hijacking detection system that is famous to save verification cost and verification latency. First of all, we should build a ground truth dataset for our machine learning training. To collect origin hijacking data, we collect events from BGP-More and validate this event with ROV, IRR, topology, and MOAS duration filters. So after the data filtering, we finally get more than 800 exact prefix origin hijacking incidents and more than 400 sub-prefix origin hijacking incidents. Then we sent emails to each victim AS in each origin hijacking incident. And based on the response, we calculate the confidence interval for our origin hijacking dataset. And the result shows that our dataset is accurate enough. And then to collect legitimate MOAS conflicts, we collect MOAS from RPKI, and then we validate the data with historical BGP data. And finally, we get about 500 exact prefix legitimate MOAS data and many sub-prefix legitimate MOAS data. So with the ground truth dataset we built, we can identify 6 dominant characteristics that can help distinguish legitimate MOAS from origin hijacking. We first found that exact prefix legitimate MOAS and sub-prefix legitimate MOAS are significantly different in some characteristics. And so we assume that exact prefix legitimate MOAS and sub-prefix legitimate MOAS are caused by different operations. First, we calculate the AIS rank value for each AIS in each MOAS event. And to divide the MOAS into 4 MOAS types, they are exact legitimate MOAS, sub-legitimate MOAS, exact origin hijacking, and sub-origin hijacking. This figure shows the rank difference for the 4 MOAS types, and we can see that the overall rank difference of exact prefix legitimate MOAS is much smaller than the other 3 MOAS types. And then we measure the proportion of different business relationships in individual MOAS types. Specifically, we identify whether the multiple ASs in a MOAS conflict are belonging to the same organization or having provider to customer relationships or having peer-to-peer relationships or are belonging to the same IXP. And in this figure, we can find that ASs in an exact prefix legitimate MOAS are more likely to be belonging to the same organization, and ASs in the sub-legitimate MOAS event are more likely to have provider to customer relationship. Then we measure the proportion of different geographical relationships in individual MOAS types. Specifically, we identify whether ASs in a MOAS event are directly adjacent or are belonging to the same country or are located in the same IR. And then we also measure the number of common neighbors, the number of common providers, and the number of common customers, and the number of common peers for multiple ASs in MOAS. And from these results, we can find that ASs in sub-legitimate MOAS are more likely to be adjacent neighbors. And legitimate MOAS are usually the two ASs in a legitimate MOAS are usually located in the same country or in the same IR. We also notice that some hijackers do not appear in global routing tables for a long time before hijacking, while legitimate ASs usually announce prefixes in daily BGP updates. So we measure the announcement stability for each AS in our ground truth dataset. And this figure shows the proportion. We can see that legitimate ASs usually have higher announcement stability, and the real hijackers ASs are usually having a lower announcement stability. We also found that the hijacker in a large hijacking incident may hijack hundreds of victims at the same time. So we also calculate the number of victims for each hijacker AS. And the results show that legitimate AS usually have lower hijacking activity, and the real hijackers usually have higher hijacking activity. We also calculate the Gini for the victims about their location in different IR. So we can find that the 6 dominant characters can help distinguish legitimate MOAS from origin hijacking. So we use a tree-based classifier to train a MOAS classifier. And we select 26 features that capture the 6 MOAS characteristics. And on our ground truth dataset, we found that all features add positive OOB accuracy, and the precision is about 95.49%. We also run the MOAS classifier in practice, and the practical recall is up to 99.2%. This means that MOAS classifier can help significantly reduce the false positives of existing control plane analysis. However, we found that in practice, the MOAS classifier is not good at the test precision in the ground truth data. So we finally propose the new system called Themis. In the Themis, we add the MOAS classifier between existing control plane analysis and existing data plane probing. So the Themis monitors BGP updates and use the prefix ownership database to identify each MOS conflict. And then each MOS conflict will be sent to the MOS classifier, and it will be identified as a legitimate MOS or a potential hijacking. Because MOS classifier has very high recall, so Themis only needs to do data plane probing for potential hijackings, so it can save high verification latency and cost. Specifically, in the first stage, we should build prefix ownership database. In addition to using historical BGP data like augurs, Themis also collects more prefix ownership information from RPKI and IRR. Then Themis monitors MOS conflicts based on the BGP updates it receives. Themis optimizes the monitor of augurs by combining historical BGP validation, ROA, and IRR validation to identify as many legitimate BGP updates as possible. And then Themis uses the MOS classifier to filter out legitimate MOS. This is the core of Themis. It classifies MOS conflicts into potential hijackings and legitimate MOS conflicts by using MOS classifier, and only potential hijackings will be sent to the data plane. Finally, Themis uses the same data plane probing and identification method as augurs to ensure detection accuracy. Our evaluation showed that Themis can achieve almost the same accuracy as augurs, while reduce more than 50% of verification cost than existing detection systems, and can significantly reduce verification latency when processing multiple concurrent MOS conflicts. This work has been accepted in Usenix Security, and more details can be found through this link. So, in the end of the presentation, I list some future research directions related to BGP security. The first is about promoting the deployment of RPKI-based validation. So, in current stage, the deployment ratio of ROA is about 50%, is pretty high, but the deployment ratio of ROA, that is the RPKI-based validation, is still low. So how to promote the deployment of ROA is still a problem, and it is the key problem. So we have related work which is accepted in NDSS 2022, and we hope that can help improve the deployment of that. And another research directions is about defense against BGP path hijacking, BGP forged origin hijacking, or BGP route leak. And they are other kinds of BGP hijacking or BGP insecurity events. And there are also many recent solutions, such as ASPAR in IETF CIDROPS working group, BGP ISAC in NDSS 2024, and DFOH in NSDI 2024. Okay, thank you everyone. Any questions?
Thanks, Lantern, for his excellent presentation. So is there any question? So no question. So thanks again, Lantern. So let's move to next presentation. The next topic is be careful of your neighbors. Injected sub-prefix hijacking invisible to public monitors. The presenter is Jun He. He is a graduate student at Tsinghua University. His research focuses on network security and network measurement with a primary emphasis on investigating security concerns related to the BGP protocol and associated measurement technologies. So let's welcome Jun He, please.
Hello everyone, my name is Tsinghua. I'm from Tsinghua University. Today I'm glad to be here to give us a speech about my research. The title is Be Careful of Your Neighbors, Injected Suffix Hijacking Invisible to Public Monitors. And I'm going to introduce our work in 4 parts. First, I will introduce the research background and the preliminary knowledge. And BGP is the current inter-domain routing protocol used by all ASs. However, there's a lack of authentication mechanism in it, so the attacker AS can forge and propagate invalid routing information to hijack legitimate traffic sent from other ASs to the victim, which is called prefix hijacking. In recent years, prefix hijacking incidents continue to occur, posing a great threat to the security of the internet. Therefore, many works have studied possible attack methods and the defense methods to promote routing security. The existing defense methods are mainly divided into 2 categories. The first category is preventive security mechanisms, such as BGP-SEC. Such as BGP-SEC, RV, etc. But these security mechanisms are too costly to deploy, and they depend on the coordination among all ASs, which is difficult to deploy fully in a short time. The second category is hijacking detection and manual mitigation after detection, but the best detection methods rely on the routing data from public road collector infrastructures, that is, route views and the reprise. Specifically, these 2 platforms established collectors to peer with some ASs and collect BGP update messages from these ASs. These ASs that provide their routing information are called monitor ASs, or monitors for short. The detection capability is largely influenced by these monitors. So many works have considered how to control the impact and the propagation of prefix hijacking to reduce the visibility to public monitors. But their proposed attack methods rely on strict attack premises. For example, special BGP communities or pre-knowledge of routing policies. It's difficult for a realistic attacker to ensure the invisibility of the attack through these methods. So in this part, we introduce our attack methods. Some works notice the existence of the hidden hijacking phenomenon, which reflects the inconsistency between the control plane and the data plane. Theoretically, the impact scope of a sub-prefix hijacking is the entire internet. That is, the invalid sub-prefix route will pollute all ASs. In fact, when the invalid route is being propagated, some ASs may not learn it due to the routing policies determined by AS relationship or the existence of other filtering mechanisms. As shown in the figure, suppose there is an invalid route of 10.1.1.0/24 and a legitimate route of 10.1.0.0/16. AS3 learns these 2 routes and propagates them to AS2. However, if AS2 deploys ROV and can filter the invalid route, then both AS2 and AS1 can only learn the legitimate route of /16. Although AS1 is not polluted, its traffic can still be hijacked. When it sends traffic to the /16 legal prefix, its traffic may pass through AS3, and then the traffic will be forwarded to the attacker due to the longest prefix matching principle. However, AS1 could not foresee this happening. From its point of view, this is a hidden hijacking. Inspired by the hidden hijacking phenomenon in BGP, we consider how to control the visibility of subprefix hijacking in a feasible way. Our attack method is called injected subprefix hijacking. The main idea is when the attacker announces invalid subprefix rules to its neighbors, it can use certain tricks to control them not to propagate outwards. Specifically, we have two implementations. The first implementation is via BGP community's attribute, as shown in figure A. Prefix P represents a legal readable prefix propagated from other ASs in the internet. Then we can see that all ASs in the figure can learn the legal rules about prefix P. Attacker ASA now advertise an invalid route for the more specific subprefix P astrophe of P to its neighbor ASN. Unlike the regular BGP update messages, it adds the no export label to the community's field. In this way, when ASN learns this invalid route, it will now advertise this route to its other neighbors. So ASD will not learn the invalid subprefix route. But when ASD sends traffic to prefix P and pass through the polluted ASN, it may be diverted to attacker ASN as shown in the red arrow line. This is a success for the attacker. The second implementation is via AS path poisoning, as shown in figure B. When the attacker ASA forge invalid subprefix route to ASN, it prepends all neighbors of ASN to the AS path field. Now the neighbors of ASN will discard these invalid routes after receiving it because they found their AS numbers are already contained in the AS path field. With these two implementations, attacker can choose to pollute only neighboring ASs that are not public monitors and then hijack legitimate traffic passing through them. In most hijacking attacks, attackers simply drop the traffic after hijacking it, similar to BGP black holing. Banani et al. Proposed a man-in-the-middle hijacking, only intercepting the traffic and then send it back to the legitimate origin AS of the attack prefix. Our proposed attack can easily achieve this extension. The attacker needs to ensure that the legal route it learned before is not affected, thus only polluting those neighbors that the legal route does not pass through, as shown in the figure. ASA only injects and pollute ASN. When ASA hijack traffic from ASN, it can send the traffic to the legal origin through ASM. This attack is even more difficult to be detected. To implement this attack via BGP communities, the attacker needs to ensure that the invalid prefix are not filtered by neighbors. In addition to deploying preventive security mechanisms, some provider ASs filter the update messages sent by their own customer ASs, accepting only those prefix that have been publicly registered or assigned to customer by themselves. To the advantage of attackers, prefix filtering mechanisms are not widely deployed at present. If the attack is carried out via AS path poisoning, in addition to prefix filtering mechanisms, it may also be affected by some AS path filtering mechanisms. For example, tier 1 ASs and many large ISPs deploy peer lock to fill out apparently invalid AS passes. Besides, very long AS path field is more likely to be filtered. But in general, both implementations are highly feasible. These attack conditions are not difficult to achieve. Next, I will show our experiment results and give a more specific analysis. We evaluated the impact of our attack through extensive simulations. The simulation method is adopted by many related works. Specifically, we use CADA's AS relationship dataset to establish the interdomain topology with the classic Rixford model to simulate the routing policy of OSs. And we use we extract information about the currently deployed monitors from the root views and the reference websites. When we analyze the attack impact mainly from two perspectives. The one is hijacking capabilities and the interception capabilities of different attackers. The other is indicators that best characterize the hijacking capability of NAS. First, because this attack method is implemented by affecting neighbors, there is a large gap in attack capabilities between ASs at different levels. While synthesis et al. Showed that prefix hijacking affecting more than 2% of global ASs is always visible to public monitors. This threshold can be easily overridden using our injected subprefix hijacking. When our attacks are completely invisible to public monitors, Tier 1 ASs, large ISPs, can hijack an average of more than 20% and more than 60% of global ASs, respectively. And in the last experiment, we found some low-level ASs have stronger attack capabilities than high-level ASs. So we try to find which indicator that is best for measuring attacker's capability. We consider three key metrics: AS degree, customer call size, and adjacent call size, which is defined as the sum of the custom call sizes of its known monitor neighbor ASs. In a world with like about 1,000 attackers ASs for each indicators with the same rankings respectively, thus constructing three attack sets to verify their differences in attack capabilities. The CDF of general hijacking capabilities of different attacker sets is shown in the figure. We can see that the adjacent call size we defined can best characterize the general attack capability of NS. In the last part, I will give a short further discussion of our attack. First, we'll discuss the resistance of our attack to various different defensive approaches. Most data plane detection approaches inherently rely on the reachability information provided by a single IP address in the target prefix, but the selected IP address may not belong to the hijacked subprefix. And the active detection overhead is very high. So these data plane approaches are not suitable for detecting subprefix hijacking. Control plane and hybrid approaches rely on the routing updates provided by public route collector infrastructures. When they find multiple origin AS conflicts in routing updates or abnormal links in AS paths, further detection procedures will be triggered. Whereas our post-attack ensures the invisibility to monitors, thus bypassing this detection approach. Though the attack we propose are difficult to defend against, there are still some methods can provide some defense. First, ASs can adopt stricter filtering policies. If the AS finds that a neighbor's update message attempts to influence its propagation, and none of these public monitors have a route for this prefix, it should verify that the neighbor is the legitimate owner of this prefix. Second, because of the special role of ROV in defending against subprefix hijacking, the deploy of ROV and RPK should be accelerated. And the ASs may consider using stricter ROA records. That is, the max length of RA should not exceed the length of the existing legal prefix. Third, deploying more monitors can somewhat reduce the general attack capability of some attackers. However, it should be noted that as long as the attacker's neighbor do not deploy monitors, there is no impact on the attacker's capability. And here are my references. Thanks for listening.
Thanks, Junhe, for his excellent presentation. So is there any question? So I have a question. you said that if we deploy more monitors, then the hijacking capability will be decreased. So if also from your data, the tier one, as they have more capabilities to do hijacking. So if our tier one SP the deployed monitors, maybe the probability can be decreased.
Yes. If the more high level ASICs deploy monitors, then the visibility of the attack is it will also be increased. So using our attack method, the attackers can hijack less ASICs in the global ASICs.
So okay, thank you again. Thanks. So let's close this session. Thank you for joining us.